Welcome to Brain Vision.
In this case, we have a beam here that's being lifted by a crane or something, and they've welded two of their little beams on it here, and then attached cables, and we've made a little triangle here up to point C for these cables, where then this goes up and the total weight of the beam and attaches to whatever crane or whatever it is. And we're told that this angle here is theta. And in the first case, we're going to look at 30 degrees. So we can see that because of symmetry, these two things have to be, or have to have their vertical components must be equal, which means that they both must be half the weight. And then because we know this angle, we can find the horizontal component, and that is just the tangent of that angle times the vertical component for this guy, and then we need a minus sign over here for this one. We can then figure out what the bending moments are, and they're going to be equal and opposite. And so we have a bending moment from the horizontal components of these. So a bending moment like this and a bending moment like this. And so those act here. So we have the vertical components acting as point loads, and then the horizontal, moments acting as point moments at these 2 points on our beam. And then we have the weight, we're assuming, is distributed uniformly over the beam. So we have this, the weight is, the weight per unit length is W divided by L, where L is 5 meters, and we had the weight was 3 kilonewtons. So we know what this distributed load is. So we take cuts here and here and here, and we can make our diagrams. So there's no shear force at the ends, so it's 0 there. And so there's a distributed load acting down, and so we have a slope on the shear diagram. We get down to minus 0.9 kilonewtons, and that's going to be our maximum magnitude will occur right at the at point F. And then we have a jump up of 1.5 kilonewtons right from that point one. Then we have again another downward slope, same slope, and we get to minus 0.6 kilonewtons. Then we have another jump of 1.5 kilonewtons up to 0.9. So we have maximum shear stresses acting at where the wires attached to the beam, and then we have another negative slope from the weight of the beam, and we get back down to 0 here. Because we have lines here, we'll have parabolas here, and we'll also have some jumps because of the point moments. So in this region we have 0.3, I think I missed the minus sign there, minus 0.3 x squared, and then we jump up by the moment that is acting at here, which we can calculate from these formulas. So we jump up this amount. What is that? About 0.433 kilonewton meters. And then we have a parabola defined by this. And then we jump back down here by equal and opposite amount here. And then we have a parabola coming up here that's defined by this. And we can see that our peak magnitude is 0.675 kilonewton meters. Here we get up to only 0.058 kilonewton meters. So again, our peak moments occur at the points where our the wires are attached to the beam. And again, we can see that we have symmetry here, as we'd expect, and anti-symmetry here. just because of the symmetry in the problem.